Picture the silence of an observatory deep in the night, when the only sound is the soft hum of telescopic drives turning mirrors toward a specific point in the sky. December 2025. The constellation Virgo slowly rises above the eastern horizon in the pre-dawn hours, and somewhere out there, among billions of stars, something hides that came from the abyss between the stars. This is not an asteroid, not space debris from our solar system. This is a visitor who has never before known the gravitational embrace of our sun, interstellar comet 3I Atlas, returning to the view of Earth's observers after its perilous journey through the inner regions of our planetary family. Write in the comments where you're watching this video from and what time it is. It's important for me to know who's with me on this quiet night, exploring the mysteries of a visitor from interstellar space. On July 1st, 2025, the Atlas Automated Telescope in Chile detected a moving point of light that didn't match any known orbit. Calculations revealed something incredible. The orbital eccentricity exceeded 1, which meant only one thing. The object arrived from interstellar space, the third confirmed interstellar visitor in human history. After the legendary Oumuamua in 2017 and Comet Borisov in 2019, 3I Atlas became a new mystery, a new message from the depths of space. But unlike its predecessors, this comet displayed features that made astronomers freeze in reverent amazement. A green coma, a bright emerald glow around the comet's nucleus, caused by the breakdown of diatomic carbon under solar radiation. This shade, like ghostly fire enveloping the elongated body of the comet, gave the object an almost mystical appearance. Spectral analysis showed unusually high levels of cyanogen and other organic molecules, a chemical composition that could tell us about the conditions in that distant stellar system from which 3I Atlas began its journey millions, perhaps billions of years ago. The elongated shape of the nucleus, resembling a giant cosmic cigar spinning around its axis, added mystery to this celestial wanderer. On October 29th, 2025, the comet passed perihelion, the closest point to the sun on its hyperbolic trajectory. During these critical hours, the object was about 120 million kilometers from our star, between the orbits of Earth and Mars. The temperature on the comet nucleus surface rose to hundreds of degrees Celsius, causing vigorous evaporation of volatile substances: water, ammonia, methane, carbon monoxide. The comet's tail stretched for millions of kilometers, directed away from the sun by solar wind and light pressure. This was the moment of maximum activity, the moment of greatest brightness, when 3I Atlas shone in the sky like a star of approximately 8th magnitude, visible in small amateur telescopes for those who knew where to look. But then came silence. After perihelion, the comet dove behind the sun from the perspective of Earth observers, becoming unavailable for direct observation. Weeks of agonizing wait. Professional astronomers calculated ephemerides, tables of the object's future positions on the celestial sphere. Space enthusiasts around the world prepared their telescopes, checked cameras, studied star charts. Because everyone knew, in early December, the comet would return. The last chance, the last window of opportunity to observe the interstellar wanderer before it forever leaves our solar system, departing into the eternal darkness between the stars. On December 1st, 2025, when the sky over Chile cleared after summer storms, the Gemini South telescopes caught a faint glow in the constellation Virgo. 3I Atlas had returned. Brightness had dropped, as models predicted. The object was now almost 200 million kilometers from the sun and continued moving away with each passing second. The comet's magnitude was approximately 9th to 10th, It was fading before our eyes, losing matter that would never return to its ancient nucleus. Each water molecule, each carbon atom leaving the comet, became part of the interplanetary medium of our system, an eternal reminder of a visitor from other worlds. The comet's coordinates in early December pointed to a region of sky between the stars Spica and Vindemiatrix in the constellation Virgo. This section of the celestial sphere was best observed in pre-dawn hours from Earth's southern hemisphere, though northern latitudes also got their few hours of visibility. Very slow, almost imperceptible movement against the background of stars. The comet was moving away from us at about 40 kilometers per second relative to the sun, but due to the enormous distance, it looked like a slow drift among motionless constellations. Professional astronomers created detailed search charts that were distributed through amateur observer networks around the world. Vera Rubin Observatory in Chile, the newest observatory with an 8-meter mirror and the widest field of view, included 3i Atlas on its priority target list. Every clear night, the giant camera with a resolution of over 3 billion pixels recorded the comet's position, its brightness, coma size, dust tail morphology. Data flowed into international databases accessible to researchers worldwide. The Very Large Telescope in Chile directed its 4 8-meter mirrors at the fading comet, obtaining high-resolution spectra, analyzing the chemical composition of emissions, trying to understand the nature of the matter that makes up this ancient body. Amateur observer networks organized round-the-clock monitoring. When the comet set for observatories in Chile, it was picked up by telescopes in Australia and New Zealand. Then observers in South Africa took over. Hundreds of people around the world, united by one goal: not to miss a single detail of the interstellar visitor's behavior. Photographs were published in real time, discussed on forums, analyzed by professionals and enthusiasts. Each image added a piece to the mosaic of understanding what 3i Atlas really is. By mid-December, the comet had moved to the border of the constellations Virgo and Libra, continuing its relentless journey south on the celestial sphere. Brightness continued to drop. 11th, then 12th magnitude. Now, reliable observation required telescopes with an aperture of at least 20 to 30 centimeters and sensitive cameras. The green coma became less noticeable. The comet's activity decreased as it moved away from the heat source, our sun. But it was precisely these weeks that provided a unique opportunity to study how an interstellar object reacts to cooling, how its structure changes, what processes occur in its depths. On December 19th, 2025, 3i Atlas will reach its closest approach to Earth, 269 million kilometers away. That distance is hard to comprehend. Light itself takes almost 15 minutes to cross that gulf. If you could fly at the speed of a jet plane, the trip would take 30 years of non-stop flight. And yet, even at this unimaginable distance, the comet will be there. A faint point of light moving through constellations humanity has watched for thousands of years. On this night, astronomers around the world will point their instruments at the same patch of sky, knowing it's the moment of closest approach, the last chance to capture the most detailed images of an object that will never return. Professional observatories created detailed observing schedules. Every clear night was worth its weight in gold. Weather, the eternal enemy of astronomers, set its own terms. Clouds over Chile could mean losing critical observing hours, but the global telescope network worked as a single organism. If a cyclone closed the sky over South American observatories, telescopes in the Canary Islands, South Africa, or the Australian desert picked up the baton. Data streamed to processing centers, where supercomputers analyzed every photon of light arriving from the ancient comet. High-resolution spectra showed absorption and emission lines from different molecules: water, carbon dioxide, methane, ammonia, cyanide compounds. 3I Atlas's path across the sky was relentless and predictable. The laws of celestial mechanics have no exceptions. The sun's mass bent space-time, steering the comet along a hyperbolic curve calculated to the second and kilometer. By December 20th, the comet entered the constellation Libra, crossing the sky at about 15 arc minutes per day, roughly half the apparent diameter of the full moon in 24 hours. To the naked eye, it was imperceptible, but long-exposure cameras recorded this movement as a slight blur against star trails. Astrometry, precise measurement of celestial positions, reached phenomenal accuracy. Each measurement refined the orbit, allowing astronomers to forecast the comet's future path weeks or even months ahead. By late December, 3 Atlas's brightness dropped to 13th magnitude. For comparison, that's about 4,000 times fainter than the faintest stars visible to the unaided eye on a perfectly dark night, far from city lights. Now, only large amateur telescopes, with mirrors at least 30 centimeters in diameter, equipped with cooled CCDs or modern CMOS sensors, could detect the comet. Exposures had to be long, 5, 10, even 15 minutes to collect enough photons and pick out the comet's faint glow against detector noise and the night sky. But enthusiasts around the world persevered. On frigid winter nights, they sat by their telescopes, patiently collecting the precious light of the interstellar wanderer. The green coma was still visible in spectral observations, though much weaker. Diatomic carbon, C2, continued to fluoresce under solar radiation, producing that characteristic greenish hue. This glow is the result of complex quantum processes in the thin gas envelope around the comet's nucleus. C2 molecules are excited by solar photons, electrons jump to higher energy levels, then fall back, emitting green light at about 510 nanometers wavelength. This color, almost identical to Earth's northern lights, gave the comet a ghostly, almost supernatural look in long-exposure images. Some observers noted the green tint seemed unusually intense for such a small, distant object, though careful photometry didn't show anything outside known comet physics. January 2026 brought new challenges. The comet kept drifting away from the Sun and Earth, its brightness dropping to 14th, then 15th magnitude. At this limit, even the biggest amateur telescopes started losing sight of the object. Professional observatories became the only source of new data. The Very Large Telescope continued collecting spectra, though the signal degraded more and more. Each spectrum required longer exposures, hours of light gathering to amass enough photons for analysis. Astronomers searched for changes in the gas and dust output, new lines appearing, old ones fading, variations signaling shifting comet activity or revealing the layered structure of its nucleus. By mid-January, the comet moved into Ophiuchus, low above the southern horizon for northern observers and high in the sky for the southern hemisphere. This meant most of the observation burden fell to southern observatories: Chile, South Africa, Australia, New Zealand. The European Southern Observatory coordinated international efforts, allocating observation time among scientific programs. Every hour was scheduled down to the minute. Photometry, spectroscopy, polarimetry, astrometry. Different tools and methods created a complementary picture, letting astronomers reconstruct the three-dimensional structure of the coma and tail, determine dust particle sizes, estimate gas emission speeds, and trace the nucleus's rotation. In February 2026, preparations began for the final act, the comet's close approach to Jupiter. On March 16th, 3I Atlas would pass within 54 million kilometers of the giant planet, a small distance on a cosmic scale, though too far for dramatic gravitational encounters. Still, this flyby presented a unique opportunity for spacecraft in the Jupiter system. NASA's Juno probe, in orbit around the giant since 2016, might try to observe the comet, though the distance was at the edge of its capabilities. More promising was the European JUICE probe, Jupiter Icy Moons Explorer, then en route to Jupiter and possibly well-positioned for observations. Trajectory calculations showed that after passing Jupiter, 3I Atlas would leave the inner solar system for good. The comet's speed relative to the Sun was over 40 kilometers per second, and Jupiter's gravity would only slightly adjust it. The comet would head for Saturn's orbit, then Uranus and Neptune, out through the Kuiper Belt, the Oort cloud, and finally into true interstellar space. In 10,000 years, it would cross the heliopause, the boundary of the Sun's influence. In 100,000 years, it would be several light years from the Sun. In 1,000,000 years, maybe it'll approach another star, enter a new planetary system, perhaps even be spotted by intelligent beings gazing up at their night sky. But for now, in these precious months from December 2025 to March 2026, the comet was ours, the object of human curiosity, scientific research, and philosophical reflection. Astronomers published early papers on preprint servers, spectral analyses, activity models, nucleus size estimates. Debates raged over the object's nature. Was it really leftover material from a planetary system around another star, or an ejected fragment from the outer region of a protostellar disk? Could its nucleus contain organic molecules, amino acids, maybe even precursors to life from another star system? There were more questions than answers, but each new batch of data added detail to the portrait of this interstellar visitor. The observer's calendar for these months became a document of nearly ritual importance. Space enthusiasts worldwide marked down key dates. December 19th, the day of closest approach to Earth. January 1st, when the comet crossed from Libra into Scorpius. February 15th, as the comet's brightness was expected to fall below the limit for most telescopes. March 16th, the Jupiter flyby. And after that, silence. The comet would pass beyond the gas giant, become too faint even for the largest telescopes, fading into the abyss. Those last images, taken at the end of March or early April 2026, would be humanity's farewell glimpse of the third known interstellar object. Years, decades could pass before the next visitor. Or maybe new all-sky surveys like the Vera Rubin Observatory will begin to detect such objects regularly, ushering in a new era of interstellar exploration. February 2026 brought a very special kind of excitement. It wasn't just ground-based telescopes tracking the receding comet. Deep in space, far beyond Earth's orbit, robotic probes prepared for an encounter with the interstellar wanderer. The European spacecraft JUICE, Jupiter, Icy Moons Explorer, was moving along its complex trajectory toward Jupiter when engineers at the Mission Center in Darmstadt received an unusual assignment: change the observation program, reorient the cameras and spectrometers, point the scientific instruments at an object that was never part of the mission's original plan. On February 3rd, new commands began uploading to the probe's onboard computer, hundreds of millions of kilometers from Earth, where radio signals take tens of minutes one way. Olivier Vitas, one of the European Space Agency project scientists, explained the difficulty of the task to journalists. JUICE was in a less than ideal position relative to the comet. The distance was over 150 million kilometers. The viewing angle was far from perfect, and the data transmission rate to Earth had dropped to critically low levels due to orbital geometry. Observations conducted from November 2nd to 25th the previous year, when the comet was closer to the Sun and more active, sat in the probe's memory, waiting their turn for transmission. Engineers calculated that at the current communication speed, the full data set wouldn't arrive on Earth until mid-February 2026. Patience became the most important virtue for everyone eager to see the interstellar comet through a spacecraft's eyes. While the world waited for JUICE data, ground telescopes continued their tireless watch. Each night brought new measurements, new spectra, new photometric points. 3I Atlas's brightness dropped to 16th magnitude, at the limit of even the largest amateur instruments. Professional observatories with 8 10-meter mirrors became the only window into the dying activity of the comet. Gas emissions weakened daily. The nucleus surface cooled. Volatile substances returned to solid state. The coma shrank. The tail thinned. The comet was preparing for a long sleep that would last millions of years as it drifted through interstellar emptiness toward an unknown destination. And yet, even in this fading state, the object continued to guard its secrets. Spectroscopic observations from the Very Large Telescope revealed unusual variations in the intensity of some emission lines: cyanogen, diatomic carbon, hydroxyl radical. Their relative concentrations changed in ways not quite predicted by standard comet activity models. Some researchers suggested this might indicate inhomogeneity in the comet nucleus composition, perhaps a layered structure where different regions contain different proportions of volatile substances. Others proposed bolder hypotheses that the chemical composition of the interstellar comet fundamentally differed from comets in our solar system, reflecting different formation conditions in a protoplanetary disk around a distant star. But there were also those who whispered about more exotic possibilities, especially in those corners of the internet where mystery and anomaly enthusiasts gathered. Forums and social media buzzed with discussion. Why did the comet show such unusual activity at great distance from the Sun? Why did its trajectory pass so close to Mars in October and Jupiter in March, as if someone had planned these encounters? Why did the green coma seem so intense, almost artificially bright in certain spectral ranges? Of course, rational scientific explanations existed for each question. High activity could result from especially high concentrations of supervolatile substances, carbon monoxide, nitrogen, methane, which evaporate even at great distances from the Sun. The trajectory was determined by celestial mechanics and initial conditions when entering the solar system millions of years ago. The green coma was simply fluorescence of diatomic carbon, a well-known phenomenon in comet physics. But scientific explanations rarely have the allure that mysteries and enigmas possess. On February 19, 2026, almost 2 months after the observations, the first batches of JUICE data began arriving at ground receiving stations. Low-resolution images, compressed and optimized for slow transmission speed, showed a faint point of light against the stars. The comet was barely visible even to the spacecraft's sensitive cameras. Distance and low activity were taking their toll. But the spectrometers recorded something more interesting. Ultraviolet observations showed emission lines of atomic oxygen and carbon in the comet's corona, a region of rarefied gas extending hundreds of thousands of kilometers around the nucleus. This data, obtained from space without interference from Earth's atmosphere, provided unique information about photodissociation processes of molecules under solar ultraviolet radiation. Each oxygen atom, each carbon atom, told the story of parent molecules: water, carbon dioxide, carbon monoxide, organic compounds, from which they were born through the destructive impact of solar radiation. By early March, 3I Atlas was already between the orbits of Mars and Jupiter, about 400 million kilometers from the Sun. Brightness dropped to 17th magnitude, several hundred times fainter than the dimmest stars visible to the naked eye. At this limit, only the planet's largest telescopes could continue tracking. The 8-meter mirrors of Gemini, the 4 8-meter telescopes of VLT working together, the 10-meter mirrors of the Keck observatories in Hawaii. These giants of modern astronomy squeezed every photon from the fading comet image. Exposures stretched for hours. Data from many nights were stacked together to achieve sufficient signal-to-noise ratio for analysis. This was work at the edge of technical capability, a demonstration of what modern observational astronomy can achieve when the target is an object of exceptional scientific value. On March 16, 2026, the moment arrived that had been awaited for months. The Jupiter flyby. The comet passed 54 million kilometers from the giant planet, too far for dramatic tidal effects or significant trajectory changes, but close enough for Jupiter's gravity to make its final correction to the interstellar wanderer's path. Calculations showed that after this encounter, the comet's speed relative to the Sun would increase by about a kilometer per second. A small change, but enough to further emphasize the hyperbolic nature of the orbit. The object would leave the solar system slightly faster than it entered, carrying away a tiny fraction of Jupiter's system's gravitational energy into interstellar space. This energy exchange, negligible for the gas giant, was our planetary system's final gift to the departing guest. The Juno spacecraft, orbiting Jupiter since 2016, attempted to observe the comet. The JunoCam camera, designed to photograph the giant planet's cloud cover, was reoriented toward 3I Atlas's predicted position. But the distance was too great, the object's brightness too low. In the resulting images, the comet was lost in detector noise, indistinguishable from random background pixel fluctuations. The JUICE probe, in a more favorable position, continued observations, accumulating data that gradually, bit by bit, transmitted to Earth across vast cosmic distances. The infrared imager tried to capture thermal radiation from the comet nucleus, estimate its temperature, size, albedo, the fraction of sunlight reflected by the surface. Each measurement was a grain of information adding to the slowly growing portrait of the interstellar object. The last reliable Earth-based observations came in late March 2026. Vera Rubin Observatory, with its wide field of view and deep sky surveys, caught the faintest glow of the comet at the limit of 18th magnitude. Its position on the sky matched calculated ephemerides to within fractions of an arc-second. The orbit had been determined with exceptional accuracy thanks to 9 months of observations. Astronomers could now predict 3I Atlas's position years ahead, though the comet had already become too faint for direct observation. By April, the object had receded beyond Jupiter's orbit. Its brightness dropped below 19th magnitude, and even the world's largest telescopes lost sight of it. The interstellar wanderer dissolved into the darkness of the outer solar system, beginning its long journey to the Kuiper belt, the Oort cloud, and beyond into true interstellar abyss. But data kept coming. JUICE continued transmitting its observation archive. Terabytes of information collected in November and March slowly flowed into European Space Agency processing centers. Image processing specialists applied sophisticated algorithms to squeeze maximum information from each frame. Spectroscopists analyzed absorption and emission lines, built chemical composition models, compared with data from other interstellar objects and solar system comets. theorists created computer simulations of comet nucleus evolution, trying to understand how the object survived millions or billions of years of solitary drift through galactic space before randomly encountering our sun's gravitational well. The work continued even as the research subject itself disappeared from direct view. First, peer-reviewed papers began appearing in professional journals. Nucleus size estimates ranged from 2 to 4 kilometers in length, an elongated body rotating around its axis with a period of about 8 hours. Albedo turned out low, around 4%. A dark surface covered with organic tars, the result of billions of years of cosmic ray bombardment in interstellar space. Chemical analysis showed enrichment in carbon and nitrogen compared to our system's comets, but the differences weren't as dramatic as some theories suggested. This hinted at the universality of planetary system formation processes. Protoplanetary disks around different stars may have similar chemical compositions determined by the fundamental chemistry of our galaxy's interstellar medium. 3I Atlas was a wanderer, but not a stranger. It was made from the same material as comets of our home, just born under a different sun. April 2026 found the scientific community in a state that could only be described as obsessed with details. The comet had vanished from direct view, but mountains of data collected over 9 months of observations were only beginning to reveal their secrets. In laboratories around the world, astronomers sat before multiple monitors, analyzing spectral lines, comparing photometric curves, building three-dimensional models of the comet coma. Each image pixel, each data point, was a grain of information about a world so far away in space and time that the human mind could barely grasp that abyss. Interstellar space between stars, not just emptiness, but an ocean of rarefied gas and dust threaded with magnetic fields and cosmic rays. A place where temperature drops to a few degrees above absolute zero, where an object can drift for millions of years without encountering anything substantial. Chemical analysis of 3I Atlas provided food for thought that stretched across weeks of scientific discussion. High-resolution spectroscopy showed the presence of water, the most common substance in the universe, a molecule made of 2 hydrogen atoms and 1 oxygen atom, a fundamental building block of life as we know it. But the water in Comet 3I Atlas had a peculiarity: the ratio of deuterium to hydrogen, the heavy isotope of hydrogen to ordinary hydrogen, turned out slightly higher than in comets of our solar system. This difference, measured in fractions of a percent, was statistically significant and hinted at different ice formation conditions in that distant protoplanetary system. Perhaps the parent star was somewhat cooler than our sun, or the comet formed in the outer, colder regions of that disk, where heavy hydrogen concentrated more efficiently. Carbon dioxide, frozen dry ice, made up a significant portion of volatile substances in the comet nucleus. When heated at perihelion, it sublimated directly from solid to gaseous state, creating powerful jets bursting from cracks and craters on the surface of the spinning nucleus. These emissions were asymmetric. One side of the comet was more active than the other, creating a reactive force that slightly changed the object's rotation. Astronomers recorded brightness variations with a period of about 8 hours. This was the rotation period of the nucleus around its axis. The elongated shape meant that as it rotated, the surface area facing the Sun and Earth changed, creating regular brightness pulsations. This data allowed not just determining the rotation period, but roughly estimating the shape, an elongated ellipsoid, possibly the result of a collision between 2 smaller bodies in the distant past, or simply a feature of matter accretion in a turbulent, protoplanetary disk. Special attention was drawn to diatomic carbon, C2, creating the characteristic green coma. The concentration of this substance turned out unusually high, much higher than most solar system comets at comparable distances from the Sun. Some researchers suggested this indicates richness in organic substances, complex carbon compounds that, when broken down by solar ultraviolet radiation, form C2. Perhaps the comet nucleus contained polycyclic aromatic hydrocarbons, complex organic molecules widespread in the interstellar medium, and could have been incorporated into the comet during its formation. These molecules, some considered precursors to biological compounds, made 3I Atlas especially interesting to astrobiologists studying the origin of life in the universe. If organic substances can form in protoplanetary disks around other stars and survive in interstellar space, then life in the universe may be far more widespread than assumed. Cyanide compounds, cyanogen and hydrogen cyanide, were also present in the comet's spectra. These substances, poisonous to Earth life, are actually important indicators of chemical processes in cold regions of space. Nitrogen, an essential element for life, rarely occurs freely in space due to the strength of the triple bond in the N2 molecule. Instead, it's often bound as ammonia or hydrogen cyanide, which form more easily in cold molecular clouds. The presence of these compounds in 3 Atlas confirmed the comet formed in cold outer regions of a protoplanetary system, where temperatures were low enough for these volatile substances to condense. Each molecule, each atom, was a witness to conditions in that distant system millions or billions of years ago. In late April 2026, a group of astronomers from Keck Observatory in Hawaii published strange results. They discovered what they called an anti-tail, a faint dust structure pointing not away from the Sun like a normal comet tail, but almost in the opposite direction. This phenomenon, though rare, was known in comet astronomy. It occurred when Earth crossed the plane of the comet's orbit, and large dust particles lagging behind the nucleus due to low ejection velocity created an optical illusion of a tail pointing toward the Sun. But the exact geometry of the anti-tail at 3I Atlas was unusual. Its brightness and extent didn't quite match standard models. Some researchers suggested this might be related to peculiarities of dust particles. Perhaps they were larger or had a different composition than typical solar system comet dust. It was precisely such anomalies, small discrepancies between observations and models, that became fodder for alternative theories. Online discussions multiplied on forums dedicated to unexplained phenomena. Why did the comet's trajectory pass so precisely by Mars and Jupiter? Coincidence or calculation? Why was activity at great distance from the Sun so high? 40 kilograms of water per second at a distance of almost 3 astronomical units, where ordinary comets should be practically inactive. Why did polarization of reflected light show an anomalously deep negative value of minus 2.7% at a 7-degree observation angle, a characteristic that puzzled even experienced comet photometry specialists? For each question, rational explanations existed, but the combination of unusual properties created ground for speculation. The artificial origin theory, of course, hung in the air. The idea that 3I Atlas might not be a natural comet, but a space probe from an extraterrestrial civilization disguised as a comet found its supporters. Proponents pointed to the unusual trajectory passing through the inner solar system and allowing hypothetical observers to study several planets at once. They drew attention to high activity, which could be controlled matter ejection for trajectory correction. They emphasized unusual chemical composition and anomalous optical properties, which in their opinion didn't find satisfactory explanation within natural comet science. The professional astronomy community was skeptical of such ideas, pointing out that extraordinary claims require extraordinary evidence and all observed properties of 3I Atlas, while unusual, fit within known comet physics with some assumptions about differences in formation conditions. The Search for Extraterrestrial Intelligence program, SETI, did indeed point its radio telescopes at the comet during maximum approach to Earth in December 2025. Antennas in West Virginia and California listen to frequencies from 1 to 10 gigahertz, searching for narrowband signals or unusual modulations that might indicate an artificial source. Observations continued several nights, accumulating hours of data. Results published in March 2026 were unambiguous. No artificial signals were detected. The comet was silent in the radio spectrum, emitting only faint thermal radio emission expected from a cold object of that size. For most scientists, this closed the question of artificial origin, but true enthusiasts of alien theories only saw confirmation of their suspicions. Of course, a sufficiently advanced civilization wouldn't broadcast signals openly. They'd use directed beams or quantum communication, invisible to our primitive instruments. By May 2026, scientific papers multiplied in specialized journals. Nature published a major review of all 3I Atlas observations with participation of hundreds of astronomers from dozens of countries. Science presented detailed chemical analysis of high-resolution spectra. The Astrophysical Journal published a series of papers on modeling the origin and evolution of the interstellar comet. Consensus formed slowly through debates and revisions, but main conclusions became clear. 3I Atlas was a natural comet ejected from its home planetary system millions of years ago by gravitational interaction with a massive planet, possibly a gas giant, analogous to our Jupiter or Saturn. It drifted through interstellar space, gradually cooling to the temperature of the cosmic microwave background, just a few degrees above absolute zero. Its surface was bombarded by cosmic rays, high-energy particles flying through the galaxy, which slowly altered the chemical composition of the surface layer, creating dark organic tars that give it low albedo. Backward trajectory modeling showed 3I Atlas likely arrived from the direction of the constellation Cygnus, from a region of sky rich in young stellar clusters. Precise determination of the parent star was impossible. Over millions of years of travel, the gravity of countless Milky Way stars repeatedly perturbed the comet's trajectory, erasing information about the initial path. But statistical analysis suggested the comet could originate from the vicinity of one of the massive stars of spectral class A or F, hotter and brighter than our Sun. Perhaps this star had already died, turning into a white dwarf, and its planetary system was destroyed in the process of stellar evolution into a red giant. 3I Atlas could be one of the last witnesses of that dead system, a relic of a planetary disk that no longer exists. This thought, that the comet might be a messenger from a long-dead world, gave the observations an almost mystical tinge. On quiet nights, when astronomers sat in dark observatory domes, listening to the whisper of telescope drives and distant hum of electronics, they pondered the fate of planetary systems, the cycles of birth and death of stars, the vastness of time and space. The comet outlived its star. Perhaps it saw worlds that no longer exist. Perhaps once, billions of years ago, life existed on one of the planets of that system, looked up at its night sky, asked the same questions about its place in the universe, and now all that remained was a cold chunk of ice and rock drifting through the abyss, randomly encountering our solar system on its eternal journey to nowhere. On summer evenings in July 2025, when news of the discovery of the third interstellar comet spread across astronomy forums and social media, something began that could only be described as a global awakening of curiosity. Thousands of people around the world, from professional astronomers to amateurs touching a telescope eyepiece for the first time. United through invisible threads of common purpose, they wanted to see the visitor from beyond our planetary family with their own eyes. Forums buzzed with discussions of coordinates, ephemerides, optimal observation times. People shared photos of their instruments, from modest 80mm refractors on city apartment balconies to impressive half-meter reflectors in private observatories under dark skies far from city lights. Everyone wanted to be part of this moment in history when humanity met a wanderer from the interstellar abyss. The international network of amateur comet observers, coordinated through online platforms and specialized telegram channels, quickly transformed into an organized force. Experienced observers shared advice with newcomers, how to properly configure a mount for tracking a slowly moving object, which filters to use to enhance the green coma, how to process images to bring out faint details against noise. Specialized groups emerged, photometrists measuring the comet's brightness each night, amateur spectroscopists with simple diffraction gratings trying to capture main emission lines, astrometrists precisely measuring the comet's position on the celestial sphere to refine the orbit. This was a grassroots movement, democratization of space research, where anyone with a telescope and clear sky could contribute to understanding the nature of the interstellar object. Mikhail from Crimea, owner of a 400mm Dobsonian telescope, spent 27 nights between August and December observing 3I Atlas. His detailed sketches of coma structure showed subtle changes from night to night, appearance and disappearance of jets, asymmetry in the glow, color variations. Elena from Novosibirsk, using a modest 200mm refractor and cooled camera, obtained a series of images later used by professional astronomers to calibrate their data. John from Australia, a veteran comet observer with 40 years of experience, said 3I Atlas was the most exciting object he'd ever observed, not because of brightness or tail beauty, but because of the realization that this chunk of ice and rock arrived from the space between stars, from depths beyond imagination. But not all observers were content with simply admiring celestial beauty. As data accumulated and scientific results were published, alternative interpretations of observed phenomena began emerging in certain circles. Why did the comet demonstrate such stable activity at enormous distances from the sun, where ordinary comets should be practically dead? Hubble Space Telescope data showed ejection of about 40 kilograms of water per second at a distance of almost 3 astronomical units from the sun. Phenomenal activity for such a small object at that distance. Standard comet physics models required very high content of supervolatile substances, carbon monoxide, nitrogen, to explain such behavior. But some enthusiasts offered more exotic explanations: controlled emissions, trajectory correction, maintaining an optimal path through the inner solar system. The artificial origin theory gained popularity in certain internet segments. They pointed to the unusual trajectory. Precise approach to Mars on October 3rd at 29 million kilometers, then perihelion passage on October 29th, and final flyby of Jupiter on March 16th, 2026. For theory supporters, this looked not like celestial mechanics coincidence, but like a carefully planned route of a research probe visiting key planets of an alien star system. They created detailed diagrams showing how a hypothetical probe could use gravitational maneuvers and controlled matter ejection to optimize its trajectory. Of course, professional astronomers pointed out that 3I Atlas's orbit was determined only by initial conditions entering the solar system and Newton's laws, that planetary encounters were a natural result of geometry, not design. The appearance of the so-called anti-tail in late April 2026 added fuel to the speculation fire. This faint dust structure, directed almost opposite to the normal tail, was captured by Keck Observatory and several large amateur instruments. Although anti-tails are a known phenomenon in comet astronomy, arising from certain observation geometry, the exact characteristics of 3I Atlas's anti-tail didn't quite match standard models. Dust particles seemed too large or were ejected at too low velocity, about 10 meters per second according to some estimates, much slower than typical comet emissions. For most scientists, this was simply an indication of unusual dust properties of the interstellar comet. For alternative theory enthusiasts, this was proof of controlled matter ejection, possibly for braking or trajectory correction. On October 19, 2025, an event occurred that sparked particularly heated discussions. The LASCO space coronagraph aboard the SOHO Solar Observatory, one of the most sensitive instruments for observing the region around the Sun, failed to detect the comet when it should have entered its field of view. The comet was more than 350 million kilometers from Earth, and theoretically should have been visible to this sensitive instrument that had discovered over 5,000 comets during its long service. But 3I Atlas remained invisible. Staff at the Solar Astronomy Laboratory of the Space Research Institute of the Russian Academy of Sciences explained this simply as distance and low object brightness. The comet was too faint even for LASCO at that distance. But on the internet, speculation immediately arose that the object deliberately hid, using the Sun's position to mask its maneuvers from ground observations. Conspiracy theories multiplied with each unusual observation. When the Europa Clipper spacecraft and the European Space Agency's Hera probe could theoretically cross the comet's ion tail in late October to early November 2025, some suggested this wasn't coincidence, but a coordinated attempt to study or even establish contact with the presumed alien probe. The fact that both missions had completely different goals — Europa Clipper was heading to Jupiter's moons, and Hera was flying to study the aftermath of the DART probe's collision with asteroid Dimorphos — was ignored or explained as cover for true intentions. The absence of public data about whether these spacecraft crossed the tail and what they found there only intensified suspicions of information concealment. The comet's age became another source of mystical interpretations. Preliminary estimates based on the degree of surface bombardment by cosmic rays and models of interstellar object evolution suggested 3I Atlas could be about 7 billion years old, 1.5 times older than Earth, older than the Sun itself. This meant the comet formed in the early galaxy when the Milky Way was younger, when second-generation stars were just beginning to enrich the interstellar medium with heavy elements synthesized in the cores of the first stars. Some theorists suggested such ancient objects might carry information about the early history of the galaxy, encoded in isotope ratios and mineral crystal structures. Bolder minds wondered, could such an ancient comet have witnessed the dawn of intelligence in the galaxy? Could it carry artifacts or messages from civilizations that existed billions of years ago and have long vanished? The SETI program, which pointed its radio telescopes at the comet in December 2025, detected no artificial signals. The comet was silent across all radio wavelengths, emitting only faint thermal radio emission expected from a cold natural object. For most scientists, this was final confirmation of 3I Atlas's natural nature, but true believers in alien origin only deepened their convictions. A sufficiently advanced civilization wouldn't broadcast primitive radio signals we could detect. They'd use quantum communication, gravitational waves, neutrino beams, or other communication methods humanity doesn't even suspect exist. The absence of a signal wasn't proof of absence of intelligence. It was merely a demonstration of our technological backwardness. In quiet observatories, far from the noise of internet discussions, astronomers continued their painstaking work. Each spectrum, Each image, each photometric measurement added to the growing data archive. Large international collaborations combined observations from dozens of telescopes, creating an unprecedentedly detailed picture of the interstellar comet's evolution over 9 months of its journey through the inner solar system. These were months of careful work, checks and rechecks, peer review, model building, and their refutation with new data. Science worked as it always works, slowly, methodically, skeptically, but inexorably approaching truth. And the truth slowly emerging from the data was simultaneously disappointing for romantics and delightful for scientists. 3I Atlas was a natural comet, unusual in many respects, but still obeying the laws of physics that humanity had so carefully studied for centuries. By summer 2026, when the comet had already dissolved into the darkness of the outer solar system, becoming inaccessible even to Earth's largest telescopes, the scientific community began taking stock. Conferences dedicated to interstellar objects gathered hundreds of researchers discussing results. Special issues of astronomy journals published dozens of papers, each illuminating a separate aspect of the comet: orbit, chemical composition, physical characteristics, origin, fate. Consensus slowly formed, though many questions remained open. The comet was real. It was natural. It was a messenger from another planetary system. It told a story about how planetary systems form around other stars, how objects are ejected into interstellar space, how they survive millions of years of drift through galactic emptiness. Each molecule in its composition, each peculiarity of its behavior, was a page in the history book of our galaxy. The winter of 2025 to 2026 was memorable not only for astronomers. In quiet planetariums around the world, people gathered to hear lectures about the interstellar comet. Children drew the green comet in school albums, trying to convey with crayons and paints that ghostly glow they saw in photographs. Science fiction writers created stories about ancient civilizations that sealed messages in the comet's icy nucleus billions of years ago. Composers wrote symphonies inspired by the lonely wanderer's journey through galactic emptiness. 3I Atlas entered not just scientific catalogs, but humanity's cultural consciousness, a reminder that we live in a dynamic universe where objects travel between stars, where the boundaries of solar systems are permeable, where encounters with visitors from unimaginably distant worlds are possible. December nights of 2025, when the comet slowly drifted through the constellation Virgo, became a time of pilgrimage for amateur astronomers. Observatories organized special observation nights, where anyone could put their eye to the eyepiece and see the faint greenish haze against the stars. Of course, most saw only a barely distinguishable speck of light, nothing like the magnificent comets with long tails from popular images. But knowing that this faint glow came from beyond our planetary family, from the space between stars, transformed simple observation into an almost spiritual experience. People stood in lines for hours, waiting for their few minutes at the telescope, to witness history, to tell children and grandchildren later. I saw an interstellar comet with my own eyes. Social media filled with photos and discussions. The hashtag 3I Atlas gathered millions of mentions by year's end. Professional astronomers patiently answered questions on popular science blogs and podcasts. Where did it come from? No one could say exactly. Backward extrapolation of the trajectory was lost in the chaos of gravitational interactions with countless Milky Way stars. Will it ever return? No, never. The hyperbolic orbit meant a one-way journey. Goodbye forever. Could it carry life? Theoretically, yes. Panspermia, the hypothesis of life transfer between worlds on comets and meteorites, remained a scientifically valid possibility, though unproven. Each answer spawned new questions. Each explanation opened new horizons of uncertainty. Educational programs used 3i Atlas as a living astronomy lesson. School children around the world calculated orbits, studied celestial mechanics with a real example, built models of the comet nucleus from foam and paint. Universities organized special courses where students analyzed real observational data, spectra, photometric curves, images. This was education through contact with living science, through participation in real research. Some of these students will become future astronomers, and they'll always remember their first serious science encounter came through studying a visitor from interstellar space that visited our system in winter 2025. But not everyone shared the scientific enthusiasm. In certain internet circles, alternative interpretations grew. Groups dedicated to finding evidence of ancient cosmic civilizations saw in 3i Atlas confirmation of their theories. Unusually high activity at great distance from the Sun was interpreted as a propulsion system working. Precise approaches to Mars and Jupiter were viewed as navigational maneuvers of an intelligent probe. The green coma was explained not by natural fluorescence of diatomic carbon, but as an artificial marker, a signal for those who know how to read it. The age of 7 billion years, older than the solar system, became proof the object was created by an ancient galactic civilization long before Earth formed. Professor Avi Loeb from Harvard University, known for his bold hypotheses about the possible artificial nature of the interstellar object Oumuamua, also spoke about 3i Atlas. He urged the scientific community not to dismiss the artificial origin hypothesis without thorough examination of all anomalies. He pointed to the coincidence of the comet's trajectory with the region of sky where in 1977, the famous "wow" radio signal was recorded. The most mysterious signal in SETI history, never repeated. Could 3i Atlas be connected to the source of that signal? Most astronomers considered this coincidence random. The sky is vast, and any object will pass through many interesting areas. But for enthusiasts, this was another clue, another piece of the puzzle. January 2026 brought a publication that sparked heated discussions. A group of researchers from several European institutes published a detailed analysis of polarization of light reflected from the comet. They discovered a deep negative polarization value, minus 2.7% at a phase angle of 7 degrees. This was extremely unusual. Most comets showed positive polarization in this angle range, or at most weak negative. Such deep negative polarization suggested very specific dust particle properties, perhaps unusually large grains, or special chemical composition, or unique particle surface structure. The authors suggested 3i Atlas dust might consist of large aggregates of organic substances, loosely bound together, creating a porous structure with unusual optical properties. This publication launched a wave of follow-up studies. Other groups revisited their data, seeking confirmation or refutation of the unusual polarization. Theorists built models of light scattering on various particle types, trying to reproduce observed values. Laboratory experiments studied comet dust analogs, irradiating them under conditions simulating interstellar space. Slowly, through debates and revisions, understanding formed that interstellar comet dust might indeed differ from solar system comet dust. Millions of years of cosmic ray bombardment in cold interstellar medium could change grain structure, create unique characteristics we're only beginning to understand. By spring 2026, when the comet had already vanished from direct view, even for the largest telescopes, consolidation of scientific results began. A large international collaboration, uniting more than 300 astronomers from 50 countries, began work on a summary paper that would compile all observations and conclusions. This was a giant project, gathering data from dozens of observatories, standardizing analysis methods, reconciling interpretations, resolving contradictory results. Weekly video conferences gathered specialists from different time zones, from Tokyo to San Francisco, to discuss every aspect of the comet. The orbital group refined the trajectory with phenomenal precision. Spectroscopists debated isotope ratios and implications for planetary system formation models. Comet dynamics specialists analyzed non-gravitational forces, reactive effects from asymmetric matter evaporation. The comet's cultural influence continued growing even after it disappeared from view. Documentaries about 3I Atlas aired on educational channels worldwide. Directors combined real comet images with computer graphics, recreating its journey through the Milky Way. Launched from a distant planetary system millions of years ago. Lonely drift through light years of emptiness. Random encounter with our sun's gravity. Bright flash of activity at perihelion. And final disappearance into the depths of the outer solar system. Science fiction got new momentum. Novels about ancient artifacts hidden in comet nuclei, about interstellar messages, about civilizations using comets as communication means across the galaxy. Artists created paintings and sculptures inspired by the image of the green coma and elongated nucleus rotating in darkness. Philosophers pondered the encounter's meaning. What does it mean for humanity to know we live in a universe where objects freely travel between stars? How alone are we if interstellar space is populated by countless wanderers, comets, asteroids, perhaps ejected planets drifting in darkness without a home star? Can life spread this way? On cold ships of ice and rock, dormant in frozen microbes, waiting for a new sun to awaken? Panspermia, not just a scientific hypothesis, but a philosophical concept suggesting life in the universe is connected by invisible threads, spreading from star to star, through intermediaries like 3I Atlas. Perhaps the first organic molecules from which Earth life ultimately arose arrived exactly this way, on an ancient comet that fell on young Earth 4 billion years ago. Religious thinkers also found in the comet a source of reflection. In ancient times, comets were perceived as omens, messages from gods, harbingers of important events. Now that science has revealed their true nature, does this mean the mystical significance has vanished? Or conversely, does knowing the comet arrived from beyond our solar family, from the abyss between stars, give it even deeper symbolic meaning? A messenger from the unknown, a reminder of cosmic infinity, of mysteries that will always exceed human understanding. In quiet cathedrals and meditation halls, people found in the 3I Atlas story a metaphor for spiritual journey, a lonely wanderer passing through alien worlds, temporarily illuminated by an alien sun, but ultimately continuing its path into eternity. By summer 2026, more than 100 papers dedicated to 3I Atlas appeared in scientific literature. They covered all aspects, from precise orbital elements to speculative theories about origin. Gradually, scientific consensus formed. The comet was a natural object, ejected from its home planetary system by gravitational interaction with a massive planet. Its unusual properties, high activity, strange dust polarization, organic enrichment, reflected different formation conditions and millions of years of evolution in interstellar space. Each anomaly had a rational explanation, though some required additional research and modeling. The artificial origin hypothesis remained on the periphery of scientific discourse, an interesting idea, but not supported by sufficient evidence. an extraordinary claim without extraordinary confirmation. Science did its work, slowly, methodically, separating facts from speculation, building understanding on a foundation of observations and testable theories. April 2026 became the month of final observations. Comet 3I Atlas had retreated beyond Jupiter's orbit, its brightness dropping below 19th magnitude, so faint that even the planet's largest telescopes struggled to distinguish it against countless distant galaxies populating the deep sky. Vera Rubin Observatory in Chile, with its 8-meter mirror and unique ability to capture vast swaths of sky in a single exposure, conducted the last observation series. Images required hours-long exposures, data from multiple nights stacked together to pick out the faintest comet glow from detector noise and distant starlight. In the final images, it appeared as a ghostly point, barely distinguishable from processing artifacts, the last whisper of light from an object forever leaving our planetary family, departing into the infinity of interstellar space. By May, the comet was more than 600 million kilometers from the Sun, beyond Jupiter's orbit, moving toward the outer solar system at about 40 kilometers per second relative to our star. This distance meant sunlight took 55 minutes to reach the comet, weak and cold, no longer capable of triggering any significant activity. Volatile substances had long returned to frozen state. The coma vanished. The tail dissolved into rarefied interplanetary space. Now it was simply a cold chunk of ice and rock, dark and still, nearly invisible, continuing its relentless journey away from us. In a year, it would reach Saturn's orbit. In 5 years, Uranus's orbit. In 10, Neptune's. And then the long journey through the Kuiper Belt and Oort cloud would begin, taking tens of thousands of years. Scientific teams continued analyzing data, collected over 9 months of active observations. Every detail mattered. Each spectral measurement added a piece to the mosaic of understanding interstellar object chemical composition. A group from the University of Arizona published a detailed study of the light curve. A graph of the comet's brightness changes over time. They found regular variations with a period of 8 hours 3 minutes, confirming rotation of the elongated nucleus. But there were also irregular brightness spikes, lasting from several hours to a day, indicating matter ejection from active regions on the surface. These ejections were asymmetric, creating weak but measurable non-gravitational forces that slightly altered the comet's orbit. Precise accounting of these forces was critically important for long-term trajectory prediction. Though, of course, once the comet traveled far enough away, such small effects would become insignificant compared to gravitational perturbations from distant stars. June brought publication of an important paper in Nature Astronomy. An international collaboration of 240 astronomers presented a comprehensive analysis of 3I Atlas's chemical composition. High-resolution spectra obtained by the Very Large Telescope and Keck Observatory were combined and carefully analyzed. The deuterium to hydrogen ratio in water ice turned out roughly twice as high as in Jupiter family comets in our solar system, but comparable to long-period comets from the Oort cloud. This was intriguing. Perhaps the interstellar comet formed in colder conditions where heavy hydrogen concentrated more efficiently, or perhaps this reflected different chemical composition of the protoplanetary disk around its parent star. Each isotope was a window to the past, telling a story about temperature, pressure, chemical reactions occurring billions of years ago in a distant stellar system. Organic substances in the comet sparked special interest among astrobiologists. Spectroscopy revealed the presence of polycyclic aromatic hydrocarbons, complex organic molecules consisting of several connected aromatic rings. These molecules are widespread in the interstellar medium, but their detection in a comet arriving from another planetary system confirmed the universality of organic chemistry in space. If such complex molecules can form and survive in protoplanetary disks around various stars, then chemical precursors to life may be far more common in the universe than previously assumed. Some of these polycyclic aromatic hydrocarbons, under the right conditions, can transform into more complex organic compounds, including amino acids, the building blocks of proteins, the foundation of Earth life. Plans for the future began forming in the scientific community. The European Space Agency was preparing the Comet Interceptor mission, with launch planned for 2029. This mission envisioned placing a spacecraft at the L2 Lagrange point of the Earth-Sun system, where it would remain on standby, awaiting detection of a new long-period comet, or, ideally, another interstellar object. When a target was identified, the probe would launch on an intercept course, conduct a close approach, perhaps release several small craft to study the comet from different angles. Experience with 3I Atlas showed how valuable such capability would be. Direct measurements of composition, structure, physical properties of an interstellar object would provide immeasurably more information than even the most detailed remote observations from Earth or near-Earth orbit. But while such missions remained in the future, scientists extracted the maximum from available data. Modeling of 3I Atlas's origin suggested the comet was ejected from its home planetary system several million years ago. The ejection mechanism was well understood. Gravitational interaction with a massive planet, probably a gas giant like our Jupiter. Such interactions regularly eject small bodies from planetary systems, populating interstellar space with enormous numbers of comets, asteroids, perhaps even rogue planets wandering in darkness without a home star. Statistical estimates suggested that at any given moment, several interstellar objects might be passing through the inner solar system, but most are too small or inactive to be noticed. Vera Rubin Observatory, which began full-scale operations in 2025, promised to dramatically change the situation. Its ability to survey all accessible sky every few nights meant future interstellar visitors would be discovered much earlier and studied in far greater detail. July 2026, 1 year since the discovery of 3I Atlas. Observatories around the world held commemorative events. Astronomers who devoted months to studying the comet gathered virtually and physically to share results, discuss future research, simply remember that exciting time when an interstellar visitor was among us. The most beautiful images were shown. The green coma against distant galaxies, the long dust tail curving under solar wind pressure, the rare anti-tail pointing almost toward the sun. Each image told a story. Each spectrum was testimony. This was a year when humanity for the third time encountered an object from beyond our planetary family. And each such encounter made us slightly wiser, slightly more humble before the vastness of space. In quiet corners of the internet, on forums dedicated to unexplained phenomena and alternative theories, discussions continued. For some, scientific explanations would never be convincing enough. Too many coincidences, too many anomalies, too many questions without complete answers. The trajectory passing by key planets, unusually high activity at great distance from the sun, strange dust polarization, age exceeding the solar system's age, connection to the sky region where the wow signal was recorded. For supporters of the artificial origin theory, each of these facts was a puzzle piece pointing to intelligent design, to an extraterrestrial civilization's probe disguised as a natural comet. Science said one thing, but intuition said another. And deep down, everyone wondered, what if? What if among thousands of natural comets one turns out to be artificial, and we miss it, failing to recognize it, because of bias toward natural explanations. By autumn 2026, 3I Atlas was already between the orbits of Saturn and Uranus, more than 1 billion kilometers from the Sun. Our star's light took over an hour and a half to reach it, weak and distant, barely distinguishable from other starlight. The temperature on the comet nucleus surface had dropped to minus 200 degrees Celsius, approaching interstellar space temperature. Cosmic rays, high-energy particles flying through the galaxy, again became the dominant source of surface impact, slowly altering the outer layer's chemical composition, creating dark organic tars. In 1,000 years, the comet would look as it did before entering the solar system. Dark, cold, silent. The brief burst of activity at perihelion would be just an episode in its multi-million-year history, a moment when ancient ice briefly came alive under the warmth of an alien sun. No one could observe the comet directly anymore. It vanished beyond the reach of even Earth's most powerful telescopes. The orbit was calculated with highest precision. Astronomers could predict 3I Atlas's position decades ahead, but seeing it was impossible. It became a ghost, existing only in celestial mechanics equations, in ephemeris tables, in memories of those who had the privilege to observe it with their own eyes or through telescope lenses. In 20,000 years, the comet will cross the heliopause, the boundary where solar wind yields to interstellar medium pressure. It will again become a truly interstellar object, free from the sun's gravitational influence. In 50,000 years, it will be a light year away from us. In 1,000,000 years, perhaps it will approach another star, enter another planetary system, perhaps be noticed by other beings gazing at their night sky with the same sense of awe and curiosity we felt. The philosophical significance of 3I Atlas's visit slowly penetrated public consciousness. We don't live in an isolated world, not in a closed system. The universe is dynamic. Objects travel between stars. Boundaries are permeable. What forms at one star can end its existence at another. Matter circulates through the galaxy in giant cycles lasting billions of years. Stars are born from molecular clouds enriched with heavy elements from previous stellar generations. Planets form from this material, carrying chemical memory of long extinguished stars. Life, perhaps, spreads the same way. On comets, meteorites, dust grains drifting through interstellar space, we're all children of stars, and not just our sun, but countless other stars whose material has mixed in the galactic cauldron over billions of years of cosmic history. In December 2026, exactly 1 year after maximum approach to Earth, the astronomy community held a virtual conference dedicated to the results of studying 3I Atlas. More than 500 researchers from 70 countries presented their work. There were sessions on chemical composition, physical properties, orbital dynamics, origin, astrobiological implications. Scientific consensus was forming, but open questions remained. Precise nucleus size from 5 to 11 kilometers, depending on estimation method, and assumed albedo. Age, possibly 7 billion years, but with large uncertainty. Parent star, probably from the Cygnus constellation region, but exact determination impossible. Each answer opened new questions. Each solved mystery spawned new enigmas. This is how science works, not reaching final truths, but gradually approaching more accurate understanding, step by step, observation by observation, theory by theory. The legacy of 3I Atlas remained in data, in papers, in memories. Thousands of gigabytes of images, spectra, photometric measurements lay in archives, accessible to future generations of researchers. Perhaps in decades, new analysis methods will extract from this data information that current scientists couldn't detect. Perhaps future theories will offer new interpretations of observed anomalies. Scientific data doesn't become obsolete. It remains forever, awaiting new perspectives, new questions, new analysis technologies. The comet left, but its trace in human knowledge will remain eternally, a reminder of that winter season, 2025 to 2026, when an interstellar wanderer briefly became our guest, allowed us to glimpse the mysteries of other worlds, other times, other possibilities of existence in this boundless, amazing universe. 2027 began with a feeling of emptiness in the astronomy community. Comet 3I Atlas had long vanished beyond the horizon of observability, dissolving into the darkness of the outer solar system, but its absence felt sharper than could be expected. Astronomers who devoted months of their lives to studying the interstellar wanderer now found themselves staring at empty patches of sky, where once a green point of light moved. Data was analyzed and reanalyzed. Papers were published one after another. Conferences continued discussing results, but the living object was gone. Only memories, records, terabytes of information in archives. It was like reading the diary of a traveler long departed into the unknown, leaving only notes about their brief visit to our world. The silence after the comet sounded louder than all the excitement during its presence. But this silence wasn't empty. It was filled with anticipation, because everyone knew 3I Atlas was the third, but not the last. Statistical models based on the frequency of interstellar object detection predicted that with current telescope capabilities, humanity should detect 1 or 2 such visitors every few years. Vera Rubin Observatory, which began full-scale operations in 2025, promised to revolutionize the situation. Its ability to survey all accessible southern sky every 3 to 4 nights meant even the faintest and fastest-moving objects wouldn't escape attention. Automated algorithms analyzed millions of images, searching for anomalies, objects moving unlike asteroids and comets of our solar system, trajectories with eccentricity greater than 1, hyperbolic orbits indicating interstellar origin. The European Space Agency accelerated development of the Comet Interceptor mission after experience with 3I Atlas. A critical design review was successfully completed in December 2024, and now engineers worked on the spacecraft's final configuration. Launch was scheduled for 2029 as a rideshare payload alongside the Aerial Space Telescope. After reaching orbit, the probe would head to the L2 Lagrange point of the Earth-Sun system, a stable gravitational point 1.5 million kilometers from Earth in the anti-solar direction. There, it would wait for 2 to 3 years, possibly longer, on standby, with instruments in sleep mode, with engines fueled, awaiting a signal. When ground observatories detected a new long-period comet, or, ideally, another interstellar object on a reachable trajectory, the Earth-based team would wake the probe, calculate an intercept trajectory, upload commands, and Comet Interceptor would begin its journey to meet the unknown. The mission's uniqueness lay in its design. Not 1 spacecraft, but 3. The main probe carried the bulk of instruments and served as carrier for 2 smaller modules. Several weeks before the comet encounter, these modules would separate, each following its own trajectory to observe the object from different angles simultaneously. This provided an unprecedented 3-dimensional picture. While one probe flew through the coma from one side, the second recorded tail structure, and the third studied the shadowed side of the nucleus. Such a multi-point configuration allowed understanding dynamic processes, how solar wind interacts with comet plasma, how jets form from active regions, how the nucleus rotates creating asymmetric structures in the coma. Experience with 3i Atlas showed the limitations of remote observations. Even Earth's largest telescopes couldn't resolve details smaller than several kilometers on the comet. A space probe flying at a distance of several hundred kilometers could see craters, cracks, color variations, individual gas and dust jets. The Japan Aerospace Exploration Agency JAXA, partner to the European Space Agency in the project, was developing one of the small modules. Their experience with the Hayabusa and Hayabusa 2 missions, probes that visited asteroids, collected samples, and returned them to Earth, made them indispensable project participants. The Japanese module carried a hydrogen thermal imager and a suite of plasma instruments capable of studying the most rarefied and extensive part of the comet atmosphere, the hydrogen corona, extending millions of kilometers around the nucleus. This corona, invisible in the optical range, was the result of water photodissociation. Solar ultraviolet broke H2O molecules into atomic hydrogen and oxygen, and light hydrogen escaped to enormous distances. Studying this corona provided information about the total water evaporation rate, about the interaction of comet material with solar wind, about the comet's mass loss over its entire life. University College London, through its Mullard Space Science Laboratory, led the mission's scientific direction. Professor Geraint Jones, the project's principal investigator, often recalled in interviews how 3i Atlas's visit changed mission planning. Before the third interstellar comet's discovery, Comet Interceptor was viewed mainly as a tool for studying long-period comets from the Oort cloud, objects approaching the Sun for the first time in millions of years. But the possibility of intercepting an interstellar object, if one were detected on a suitable trajectory, now became an equal goal. Instruments were optimized to detect differences between our system's comets and interstellar visitors, spectrometers tuned to search for exotic isotope ratios, magnetometers ready to study the interaction of the comet's magnetic field with the interplanetary magnetic field, high-resolution cameras aimed at revealing surface mineralogical characteristics that could tell about the distant object's parent star. Comet Interceptor project funding from the United Kingdom amounted to £16 million in national contribution, supplementing mandatory contributions through European Space Agency membership. These funds supported development of two critically important instruments: the immerse infrared spectrometer, created at Oxford University, and the magnetometer based at Imperial College London. Infrared spectroscopy was key to studying organic substances in the comet, complex carbon compounds invisible in the optical range but with characteristic signatures in the mid-infrared. If an interstellar comet contained prebiotic molecules, amino acids, nucleotides, sugars, the infrared spectrometer could detect them, opening a window to understanding how universal the chemical precursors to life are in our galaxy. Parallel to Comet Interceptor preparation, the astronomy community refined methods for early detection of interstellar objects. Experience with Oumuamua in 2017 was a painful lesson. The object was discovered already after perihelion passage, when it was receding from the Sun, and time for detailed observations was catastrophically limited. Comet Borisov in 2019 was spotted earlier, giving several months for study. 3i Atlas, discovered July 1, 2025 by the Atlas telescope in Chile, was found 4 months before perihelion, enough time to coordinate international observing campaigns, but insufficient to launch a space mission. Future sky survey systems promised to detect such objects even earlier, perhaps a year or more before perihelion, opening a window of opportunity for rapid response missions. The China National Space Administration announced plans to develop its own mission for studying interstellar objects. The project was at an early conceptual stage, but ambitions were clear. Create a probe capable not just of flying past an interstellar comet, but of accompanying it for months, studying activity evolution as it approaches and recedes from the sun. Technically, this was extremely challenging, requiring enormous fuel reserves to match velocity with a fast-moving object on a hyperbolic orbit. But if successful, science would gain an unprecedentedly detailed picture of an interstellar comet's life cycle, from cold, inert state through bright activity, burst back to frozen sleep. International cooperation was discussed, perhaps combining European, Japanese, American, and Chinese resources could make such an ambitious mission reality. In academic circles, a new astronomy subdiscipline was forming, the study of interstellar objects, or interstellar planetology. Universities began offering specialized courses where students studied hyperbolic orbit dynamics, interstellar medium chemistry, methods for detecting fast-moving objects, statistics of the wanderer population between stars. Young researchers defended dissertations analyzing data from Oumuamua, Borisov, and 3I Atlas, building models of the origin and evolution of these mysterious visitors. Grants were allocated for theoretical research. How many objects are ejected from a typical planetary system during its formation? How they're distributed across the galaxy? What the detection probability is given telescope sensitivity? Could some be captured by the sun's gravity and become permanent members of our planetary family? Philosophical discussions about the meaning of interstellar encounters continued in popular science literature and specialized publications. Carl Sagan once wrote that we're made of star stuff. Heavy elements in our bodies were synthesized in the cores of long-dead stars and scattered by supernova explosions. But interstellar comets added a new dimension to this idea. We're connected not only through common chemical heritage, but through physical matter exchange between planetary systems. Perhaps some carbon atom in your body was once part of a comet from another stellar system that fell on young Earth 4 billion years ago. Perhaps the first organic molecules from which life arose arrived exactly this way. Panspermia, not just a hypothesis, but a cosmic reality connecting all planetary systems in the galaxy through invisible threads of common heritage. Educational programs used the 3I Atlas legacy to inspire a new generation of scientists. School children calculated interstellar object orbits in physics classes. University students analyzed real comet spectra, learning to interpret emission lines and isotope ratios. Planetariums worldwide created special programs recreating 3I Atlas's journey through the solar system in an immersive dome environment, where viewers felt themselves floating in space beside the ancient comet. Documentaries won international awards for science popularization. Books were written not only for specialists, but for the general public, explaining complex astronomy in accessible language, making the mysteries of interstellar space understandable to every curious mind. By the end of 2027, scientific databases contained more than 200 peer-reviewed papers dedicated to 3I Atlas. This object became one of the most thoroughly studied in astronomy history, despite the brevity of its visit, or perhaps because of the brevity, knowing it was the only chance forced the scientific community to mobilize all available resources. Every telescope that could observe the comet did so. Every instrument capable of measuring something was used maximally. This was a moment in science history when humanity united in common purpose to understand a messenger from another world before it forever disappeared into the abyss from which it came. And in this unity, in this mobilization of intellect and technology, there was something deeply human, our unquenchable curiosity, our drive to understand, our refusal to accept the boundaries of the unknown without a fight. The night sky no longer seemed unchanging after 3I Atlas. Everyone who followed the comet now knew that stars aren't just distant lights on heaven's dome, but sons of other worlds, some with planetary systems from which visitors sometimes arrive. The space between stars isn't emptiness, but an ocean populated by countless wanderers, most of whom we'll never see, but some of whom randomly cross our path. We live in a dynamic, interconnected galaxy where matter circulates, where boundaries are permeable, where it's possible to receive word from worlds so distant in time and space that the mind struggles to grasp this abyss. And this knowledge changed something fundamental in human self-perception. We're not isolated inhabitants of a lonely planet around an ordinary star, but part of a great galactic community of worlds, bound by common history, common chemistry, perhaps common destiny. 2028 met humanity changed in an invisible way. On the surface, everything remained the same. Cities continued to grow, technology advanced, life flowed on. But in quiet observatories, in university lecture halls, in the hearts of those who followed 3i Atlas, something intangible remained, the realization that we're not alone in our isolation. The solar system isn't an island in the cosmic ocean, but rather a waypoint on the ancient trade routes of the galaxy, where matter travels between stars on ships of ice and rock, carrying messages about worlds we'll never see. This knowledge changed something fundamental in the collective consciousness, not dramatically, not revolutionarily, but deeply and indelibly. The night sky ceased being merely decoration and became a window into a living, breathing universe. In planetariums around the world, programs about 3i Atlas continued drawing full houses even years after the comet's disappearance. People came with families, brought children to show them the recreated journey of the interstellar wanderer through the inner regions of our planetary system. Computer graphics, based on real observational data, brought the comet to life. The rotating elongated nucleus, green coma, streaming dust tail. The narrator's voice, calm and measured, told the story of an object older than Earth, having survived billions of years of solitary drift through galactic emptiness. Children looked up at the planetarium dome with wide-open eyes, absorbing scales of time and space their minds were only beginning to grasp. Some of these children would become future astronomers, and they'd always remember that moment in the dark planetarium hall when space first became real for them. Literature continued exploring the theme of interstellar encounters. Novelists created stories about ancient civilizations using comets as libraries, sealing knowledge in crystalline ice structures, calculating that in millions of years, these messages would be found by other intelligent beings. Poets wrote about the loneliness of a cosmic wanderer, about the silence of journey through light years of emptiness, about the brief flash of light and warmth when meeting an alien sun. Philosophers pondered the nature of identity. Was the comet the same object after millions of years of travel? Or did cosmic rays and interstellar erosion slowly transform it into something else? This was a cosmic version of the Ship of Theseus paradox. If every atom on the surface is replaced by radiation, does the object remain itself? Musical composers found inspiration in the comet's data. One avant-garde composer from Iceland created a symphony where each instrument represented a spectral line from 3i Atlas observations. Hydrogen sounded like the low string of a double bass. Oxygen, high flute notes. Carbon created cello melodies. Cyanogen added dissonant horn chords. The result was strange, almost alien, but had its own beauty. Music literally composed from an interstellar object, translation of astronomical data into sound waves. The premiere at Reykjavik's concert hall drew a full house of listeners, many of whom wept without understanding why, simply feeling connection to something infinitely vast and ancient. Art galleries worldwide organized exhibitions inspired by the comet. Photographers displayed their best shots: the green coma against distant galaxies, the tail curving through a star field, rare frames of the anti-tail. Painters created abstract interpretations of the journey through interstellar space, cold blue and violet tones of eternal night, interrupted by sudden bursts of warm orange and yellow hues when approaching the sun. Sculptors worked with meteorites, creating physical embodiments of cosmic wanderers. One installation in Berlin consisted of thousands of small mirror fragments suspended on invisible threads, slowly rotating in a darkened hall, reflecting light rays in unpredictable directions, a metaphor for comets scattering sunlight in interplanetary space. In academic circles, work continued on understanding the population of interstellar objects in the galaxy. Statistical models suggested that at any given moment, 10 to 100 such objects pass through the inner solar system, but the vast majority are too small or inactive for detection by modern telescopes. Vera Rubin Observatory, conducting its legacy survey of space and time, promised to radically change the situation. By 2030, discovery of several new interstellar visitors was expected. Each would be a unique window into another planetary system, another epoch of galactic history. The data collection would grow, allowing statistical analysis. How do comets from different galaxy regions differ? Are there systematic differences in chemical composition? What does this tell us about the evolution of star formation in the Milky Way? Educational initiatives launched during 3I Atlas's visit continued bearing fruit. Universities reported growth in students choosing astronomy and planetary science as majors. Many cited the comet as their inspiration, that moment when abstract science became a living story, unfolding in real time. Exchange programs between universities in different countries expanded, creating an international network of young researchers united by common interest in interstellar objects. Summer schools were organized at observatories where students learned to work with real data, analyze spectra, build orbit models, interpret observations. This was a new generation, growing up in an era when interstellar visitors ceased being theoretical possibility and became observable reality. Technological development stimulated by studying 3I Atlas found applications in other fields. Algorithms for detecting fast-moving objects, developed for searching comets with hyperbolic orbits, were used for tracking space debris in Earth orbit. Methods for spectroscopy of ultra-faint objects were applied to studying distant exoplanets. Image processing techniques allowing extraction of faint structures from noise found application in medical imaging. Science rarely develops in isolation. A breakthrough in one area creates tools and methods that revolutionize others. The comet's legacy lived not only in astronomical data, but in technological innovations spawned by the drive to understand it. Religious and spiritual communities continued reflecting on theological implications of interstellar encounters. If life can spread between stars on comets, what does this mean for concepts of creation and the uniqueness of Earth life? If the universe is populated by countless worlds, some of which may contain intelligent life, how does this affect understanding of humanity's place in the divine plan? Different traditions gave different answers, but a common theme was expansion of cosmological vision, God creating not one world, but countless multitudes, each with its own history, its own destiny. Some theologians saw in interstellar comets a physical embodiment of divine connectedness, all worlds linked through matter exchange, all parts of the great creation touching through intermediaries of ice and rock. By spring 2028, the first dissertations based exclusively on 3I Atlas data appeared. Young researchers defended doctoral works analyzing every aspect of the comet with unprecedented detail. One dissertation at California Institute of Technology was devoted exclusively to modeling dust dynamics, how particles of various sizes are ejected from the surface, how they're accelerated by solar radiation, how the complex tail structure forms. Another work at Leiden University focused on isotope ratios, trying to constrain possible formation conditions of the comet and parent star characteristics. A third dissertation at the University of Tokyo analyzed brightness variations, building a detailed model of nucleus shape and rotation. Each work was a brick in the growing edifice of understanding interstellar objects. Philosophical literature explored the concept of cosmic monument. Comet 3E Atlas became a kind of monument to an unknown world, perhaps a long-destroyed planetary system, perhaps a star that had already died. We'll never know exactly where it came from, never see its home world, never know if there was life there, if there were beings who looked at this comet in their night sky, just as we looked at it in ours. But the very fact of its existence was testimony. Somewhere out there, in the depths of time and space, other worlds existed, and one of their children randomly wandered into our home. This was a meeting across an abyss impossible to bridge any other way. No signals, no ships will cross the light years separating stars in the foreseeable future. But comets travel, slowly, patiently, carrying within themselves the chemical memory of the worlds of their birth. In summer 2028, a group of enthusiasts installed a memorial plaque at Atlas Observatory in Chile, the site of the comet's discovery. Engraved on it were 3I Atlas's orbital elements, dates of key events, a brief description of scientific significance. The dedication ceremony gathered astronomers from around the world, many of whom devoted months to studying the comet. They stood under the starry sky of the southern hemisphere, looked upward, knowing that somewhere out there, far beyond Neptune's orbit, the comet continues its path away from us. In tens of thousands of years, it will leave the sun's gravitational influence. In hundreds of thousands of years, it will be light years away. In millions of years, perhaps it will enter another planetary system, and other beings will look at it with the same awe and curiosity. And maybe they too will install a plaque, remembering the visit of a wanderer that came from the direction of a small yellow star, where once existed a civilization that looked at the sky and dreamed of the stars. The legacy of 3I Atlas wasn't in dramatic discoveries or revolutionary theories, but in the quiet expansion of understanding. We live in a galaxy where boundaries are permeable, where matter circulates between stars, where encounters with messengers from other worlds are possible. This knowledge changed human perspective in an elusive but fundamental way. We're part of something larger, not an isolated oasis of life in a hostile void, but one node in a vast network of worlds bound by common history, common chemistry, perhaps common destiny. The comet came and went, but the echo of its visit continued spreading through human culture, science, art, philosophy. In this echo was memory of that winter season when for a brief time the boundaries between us and infinity became slightly thinner, and we glimpsed mysteries that will always be greater than our understanding. 2030, 5 years since the last direct observations of 3I Atlas. The comet is somewhere between the orbits of Uranus and Neptune, cold and invisible, continuing its relentless drift away from the sun at more than 40 kilometers per second. No one can see it. It's become too faint, too distant, dissolved into the infinity of the outer solar system. But astronomers know exactly where it is at every moment. The orbit was calculated with phenomenal precision. 9 months of intensive observations provided enough data to predict the comet's position centuries ahead. In computer databases at observatories around the world, ephemeris tables show its coordinates on the celestial sphere for every day, every hour, a ghostly object existing only in equations and memory. On quiet nights, when astronomers sit at their telescopes studying other objects, they sometimes point their instruments toward that region of sky where, according to calculations, 3-eye Atlas should be. Of course, they see nothing. Even the world's largest telescopes can't detect an object that size at that distance, emitting only reflected sunlight that became unimaginably faint after traveling billions of kilometers there and back. But the very act of pointing the telescope has almost ritual significance. A farewell to a guest who briefly illuminated our skies, a reminder of the brevity of the encounter and the eternity of parting. Some call this sentimentality, unbecoming of rigorous science. But even scientists are human, and the encounter with an interstellar wanderer touches something deep in the human soul. By 2030, Vera Rubin Observatory had detected 2 more interstellar objects passing through the solar system. One was a small asteroid, just a few hundred meters across, dark and inactive, spotted only thanks to the incredible sensitivity of new survey systems. The other turned out to be a comet, smaller and less active than 3-eye Atlas, but still providing valuable data for comparative analysis. Each new detection added a piece to the mosaic of understanding the interstellar object population. It became clear the galaxy is populated by countless such wanderers, ejected from their home planetary systems, drifting through light years of emptiness, randomly crossing other stellar systems on their eternal journey to nowhere. We don't live in an isolated world, but at a crossroads of cosmic highways where guests from distant worlds constantly pass through. The Comet Interceptor mission was preparing for launch in 2031. Engineers conducted final system tests, checking every component, every sensor, every engine. The spacecraft would wait at the Lagrange point for years, perhaps a decade, in cold sleep, until ground observatories detected a suitable target, a new long-period comet from the Oort cloud or, ideally, another interstellar visitor on a reachable trajectory. Experience with 3-eye Atlas showed the value of such encounters. Each interstellar object is a window into another planetary system, into different formation conditions, into another epoch of galactic history. Direct measurements from close range would provide information unattainable by any remote observations. The possibility of collecting dust samples from an interstellar comet's tail, analyzing them in a laboratory. This was a dream that could become reality in coming decades. In universities around the world, a new generation of students studied 3-eye Atlas data as part of standard planetary science courses. The comet became a textbook classic, an illustration of interstellar travel, demonstration of orbit determination methods, a data source for laboratory work on spectral analysis. Professors displayed images of the green coma on lecture hall screens, explained the physics of diatomic carbon fluorescence, discussed unusual dust properties and possible interpretations. Students wrote term papers analyzing various aspects of the comet, learning to apply the scientific method to real data. Some of these students would become the astronomers who study the 4th, 5th, 10th interstellar object. The legacy of 3-eye Atlas lived in knowledge and inspiration passed to future generations. The comet's cultural influence continued manifesting in unexpected ways. A composer from Japan created an opera based on the imagined history of the comet, from formation in a protoplanetary disk around a distant star billions of years ago, through catastrophic ejection by gravitational interaction with a giant planet, long eons of solitary drift through interstellar darkness, random encounter with our solar system, bright flash of life at perihelion, and final disappearance back into eternity. The libretto was in a mix of Japanese and an artificial language meant to represent the voice of the comet itself. The music combined traditional instruments with electronic sounds and processed astronomical data. The Tokyo premiere drew an international audience. Critics called the work a meditation on themes of time, loneliness, and the brevity of encounters in the infinite universe. Philosophers continued pondering the metaphysical consequences of interstellar encounters. If comets travel between stars, carrying matter from one planetary system to another, then the concept of isolated worlds becomes an illusion. All planetary systems in the galaxy are connected through this slow but continuous matter exchange. The atoms composing your body may have traveled through light years before arriving on Earth. The chemistry of life may be universal, not just because chemistry laws are the same everywhere, which is also true, but because the very material of life circulates through the galaxy, mixes, redistributes, creates connections between worlds at the most fundamental level. We're all children not of one star, but of many, heirs to a galactic history spanning billions of years. In ancient religious texts, comets were often interpreted as omens, divine messages. Modern science revealed their physical nature: chunks of ice and rock, remnants of planetary system formation. But interstellar comets added a new dimension to ancient awe. These truly are messengers, though not from gods, but from worlds so distant and ancient that minds can barely grasp them. Each interstellar comet is a message written in the language of chemistry and physics, telling a story about a place and time we'll never see directly. Scientific understanding doesn't diminish the sense of awe. It deepens it, adding layers of meaning to the simple act of observing a faint point of light in the night sky. By 2035, 3I Atlas is beyond Neptune's orbit, more than 5 billion kilometers from the Sun. In 50 years, it will reach the inner regions of the Oort cloud, the spherical shell of comets surrounding the solar system at distances of tens of thousands of astronomical units. But unlike Oort cloud comets, gravitationally bound to the Sun, 3I Atlas will pass through this region without slowing, continuing its journey to true interstellar space. In 20,000 years, it will cross the heliopause, the boundary where solar wind yields to interstellar medium pressure. In 50,000 years, it will be a light year away. In 1,000,000 years, perhaps it will approach another star, perhaps enter another planetary system, where other beings, if they exist, will look at it with the same awe and curiosity we felt. In the silence of cosmic night, where temperature is just a few degrees above absolute zero, where matter density is 1 atom per cubic centimeter, where the only energy source is rare cosmic rays flying through the galaxy, the comet continues its journey. It doesn't know about the attention it received during 9 months of 2025 to 26. It doesn't remember the sun's warmth that triggered a brief activity burst at perihelion. It simply exists, cold and still, obeying physics laws, moving along a trajectory determined by initial conditions millions of years ago, but in the hearts and minds of people on a small blue planet around an ordinary yellow star, memory of the comet lives, woven into culture, science, art, philosophy. Memory of that time when the boundaries between us and infinity became slightly thinner, when we received word from worlds beyond our understanding. The night sky will never be the same again for those who know. Every star, a possible home to a planetary system. Every planetary system, a source of comets, asteroids, perhaps rogue planets ejected into interstellar space. Between stars exists an invisible ocean of wanderers, most of whom we'll never detect, but some of whom randomly cross our path. And each such encounter is a gift, an opportunity to glimpse the mysteries of other worlds, other times, other possibilities of existence in this boundless, amazing universe. 3I Atlas came and went, but the echo of its visit continues to resonate, reminding us we're part of something unimaginably larger, a galactic community of worlds bound by common past, common chemistry, common destiny in this great cosmic dance lasting billions of years and stretching across distances that will forever remain greater than our ability to cross them, but not greater than our ability to understand and dream about them. And somewhere out there, in the cold darkness between stars, the comet continues its journey, a silent witness to worlds that no longer exist, a messenger from times that will never return, a wanderer of eternity who briefly touched our lives